Let's talk about the ideal gas law. So so we're going to kind of go through this part of the notes right here. Before we talked about the combined gas laws and all of these individual gas laws. And remember, in chemistry and science, law just means like equation, a mathematical equation that expresses something about the physical universe, or the physical or chemical and the chemical world. We also talked about the kinetic molecular theory. So if you'll notice with all of these all are relationships. What is the connection between pressure and volume? They are inversely proportional. There is a connection between the two. If you change one, the other will also change in response to that. If you put all of these together, you end up with this combined gas law. And these are all really great and useful. But they're limited in that there has to be a change. So you have to have an initial situation that you understand, a change to that situation, and how do the other variables interact? That's great. But what if you just have gas and you just want to know just information about that gas? Like, what is the pressure, volume, temperature, and moles of a gas that isn't changing, that's just sitting there? You have a balloon of helium. What's happening with this helium? Well, from a mathematical standpoint, there is something that you can do. If you do enough experiments and you figure out some calculations, you can turn this equation, this combined gas law, instead of comparing two different scenarios, the pressure, volume, moles, and temperature, instead of just the change, you can concretely tie it to just one situation. But you're going to need a constant. So if you kind of think about this like, think about it like when you're trying to solve for the equation for the slope of a line, how you have a slope, or the equation for a line, sorry. The slope is essentially the constant. It's like, we know that, as if you've got like, a positive slope, as X increases, so does Y, but how much? This is very descriptive, but it doesn't give you like a concrete number. Does it change? If X changes a lot, does Y also change a lot, or does Y only change a little bit? That's like what a slope represents. And it's a constant. So in math and chemical equations, mathematical or like physical or science equations, we need constants. It's just kind of part of the mathematical language. So if you solve for the constant, you end up with this equation right here. It's PV equals nRT. This is a mathematical expression of the kinetic molecular theory and a consolidation of all those variable relationships into one glorious, perfect, beautiful equation. Now, this equation only works for ideal gases, which is what these are. Kinetic molecular theory tells you things that are generally true about gases. That's why we call it the ideal gas law. It's an ideal. It's not reality. Real gases aren't ideal gases. But most of the time, these assumptions are close enough, especially at like relatively low pressures and large volumes and higher temperatures. If you get to gases that are really low temperature, taking up less volume, and especially if the gases have a lot of attractive forces between each other, the ideal gas law won't quite work. But for our purposes, it's totally fine. We can assume that most gases are ideal gases, and this will work out. It really works out great. So let's talk about this. This equation has 5 variables: P, V, N, R, and T. So let's break down what each of those are. P stands for pressure, which is measured in atmospheres. V stands for volume, which is measured in liters. K or T stands for temperature, which is measured in Kelvin. N stands for number of molecules, also known as moles. And R is the gas law constant. This funky, weird looking thing, this whole thing. So you'll notice how this is a unit. This is a number with its unit. This whole thing is R. Every single time you have to include that entire thing. That whole number with those weird units is R. K constants, these constants, whether they're R or whatever, constants always have weird units to them. It's just kind of like part of the thing because they have to cancel out all the other units that are in the equation. So what this means is that it's liters atmospheres per mole K. So I call it LATMA mole because that's just how I remember it. So it's always liters per atmospheres per mole K. It's 0.082057. This is the number that was mathematically calculated. It's related to moles, the definition of a mole. It's also related to the definition of like absolute zero. It's a whole thing. A lot of physical chemistry involved in all of this. So the way that this equation works is as long as there are four main variables with gases, as we know at this point: pressure, volume, temperature, and moles. If you know three of them, you can use this equation to solve for the fourth. So if you know the pressure and the volume of the moles, you can solve for temperature. If you want to know the volume of a gas, as long as you know the pressure, the moles, and the temperature, you can solve for the volume of a gas. It's pretty much that simple. So let's give this a try. Oh, another quick note, the R is a variable and you have to use it, but it's constant. It does not change. It is always this number with these crazy units. So you always know the R, you have to use it, but we just don't really include it in the equation because it's kind of messy. I will always give it to you. You don't have to memorize it, although you probably will. I like to call this equation PERVNERT or PIVNERT because the PVNRT, that's just how I remember it. I like PERVNERT. I don't know why. I think it's all the retroflexed R's because of English. Just like lots of R's in it. Just sounds really stupid. It just sounds goofy and I like it. But PIVNERT works as well. So just like we call MCAT, the Q equals MC delta T, we call it the MCAT equation. It's just a way of like saying it faster. This is PERVNERT. So if you hear me say PERVNERT, it means use this freaking equation. Let's do it. So here's an example. At what temperature will 0.654 moles of neon gas occupy 12.3 liters at 1.95 atmospheres? So looking at the information we've been given, we are trying to solve for temperature, which is going to be in Kelvin. We have been given moles, which is N, liters is volume, and atmosphere is pressure. So we have P, V, N. We're solving for T. We have R right here. So let's just go ahead and figure this out. So here's our equation, PV equals N R over T. We are solving, I'm just gonna grab this red marker or maybe purple. This little color is nice on these. We are trying to solve for T. This is the variable we want. So same procedure as always. Let's algebraically rearrange the equation so that it's all set up. I'm going to divide each side by NR. That cancels, that cancels. So we're going to have temperature is going to be equal to PV over NR. Now all we got to do is plug in our numbers. So our pressure is 1.95 atmospheres. Our volume is 12.30 liters. Our moles are 0.654 moles. And our R is this crazy number. So watch how I do this. This can be a little confusing. That's how you do it. Okay. Some people have this tendency to think that that this is like variables in an equation. So they'll like put the liters, they'll put like 12.3 here and they'll just like add the same numbers twice and it doesn't work out. No. These are the units for this number. Every single number here has a unit, and that's always important when we're doing any of these, any of these chemistry, or if you move on to physics problems. Every single number you ever have, with a few exceptions, should have a unit. Sorry, I'm in equilibrium with my AP chemistry kids right now. And technically, we have KSPs, which are K's. We have a different type of constant that doesn't have a unit, but most numbers have units. Include them. Do it. It's good. So let's see what happens with these units and why this is important. Liter atmosphere per mole. Okay, perfect. So let's see what cancels out here. I've got atmospheres is up here and also here, so those cancel. I got liters and liters, that cancels. I've got moles, and that cancels. The only thing left is K. So the reason that this number has these weird units is it's specifically because it has to cancel out all the other units. So K is the only unit left. And that is our, that's exactly what we need for temperature. We need Kelvin. So that's perfect. So now all we need to do is just do the math. So it looks like this is going to be 1.95. Oops, not 1 negative 95, 1.95. Nope, I did it again. Times, what is that? 12.3 divided by, was that, it was 0.6, wasn't it? My handwriting is not the best. 0.654. Let's see if I can write that a little bit better. Yeah, it's a bit better. Yep, 0.654. Also divided by, just remember this is also on the bottom, so make sure you're dividing that number. You can also do like parentheses 12 point or parentheses divided by parentheses 0.65 times 0.0825, whatever parentheses, but this works. I'll show you the other way. Divided by 0.082057. That's our number. Okay, so that's our temperature. I'll show you the other way of entering it just in case you're curious. That's not how to do it. The calculator's not going to like that. If you put this in parentheses, you can enter it straight up as you see it. 82057. I haven't quite memorized it yet, but I will. Perfect. Yep, same answer. Okay, so you can see there's two different ways of entering it. But just make sure you divide and you'll be fine. Okay, so the answer is 446.94 Kelvin. Just out of curiosity, let's see what that is in Celsius. I think to get to Celsius, we just have to subtract out 273, right? Let's see. To get Kelvin, Celsius is Kelvin minus 273, yeah, for sure. So just if you're curious, that's 173.94 degrees Celsius. They're the same thing. You didn't have to convert it, but you could if you wanted. And that's in Fahrenheit, what would that be? Yeah, it's like oven temperature, like maybe 200 or so, something in that range, maybe 300. No, it's above the boiling point of water, which is like 300 and something. So yeah, it's like 400 or maybe 500 degrees Fahrenheit, something like that. Definitely within oven temperature. So there you go. That's how you do it. So let's go to the unit packet and just see some examples of this. For the unit packet, you are now going to be able to work on a lot. The first one is page 4. Page 4 is interesting because it has a mixture of the combined gas laws, which are these guys, these ones here, these lovely little equations there, and also this one. So the hardest thing here, like it says, is just knowing which equation to use. So you kind of think about what information are you given and which equation is going to work for the information you're given and the information you want, is piecing those together. Page 5 is all just ideal gas law. Let me just take a look. We're gonna have quite a few pages of this, y'all. This is a big deal. Page 6 and page 7 is more of that. Let's see what else we got here. Page 8. Yeah, up to page 8. So all the way from page, like I guess that's 4 to 8 is all the worksheets, pages that you have to do. So let's do a couple as an example, and then you guys will all get to work on it, and you'll be able to use the answer key and all that, and we'll go over some more in class if you need help. Okay, so I like number 1. This is great. So how many moles of a gas? Oh, here's another thing. The gas doesn't matter. Doesn't matter if you add up all the gases. Gases basically all act the same way. So it doesn't matter if it's chlorine gas or hydrogen gas or helium gas or ethanol gas. It's all just gas. The identity does not matter. So how many moles of gas does it take to occupy 120 liters at a pressure of 2.3 atmospheres and a temperature of 340 K? So this is great. Perv nerd. For sure. It looks like we are solving for moles. So let's divide each side by RT. So moles is equal to PV over RT. So pressure is 2.3 atmospheres. Volume is 120 liters. R is 0.082057. Look, It didn't take me that long to memorize it. I told you. Sorry. I'm very used to this number. It's just one of these numbers that I just know. You know, you do these problems enough and you just kind of memorize them. Pretty funny. Anyway, and again, what's the unit? Latma molx, liter atmosphere per mole K. That's how I remember it. You know, I've been doing this for about as long as you all have been alive. So, you know, it gets ingrained in your head at a certain point. And then temperature is 340 K. Now it's really important that this is in Kelvin. Luckily for us, it's already given to us in Kelvin, so we don't have to worry about it. Let's cancel out our units. I see liters and liters twice. I see atmospheres and atmospheres twice. I see K, and I'm left with moles, which is what I'm solving for. So that's perfect. So now we just got to run it through a calculator. 2.3 times 120 divided by 0.08 2057. Also divided by 340. It's going to be equal to 9.89 moles. Et voila, that's our answer. Okay. Let's try another one out. You guys can always try it first, you know, pause the video. I would recommend that and give it a try yourself and then see if you get the same answer as I do. A lot of times your setup and your answer might not be the same as, if your setup is the same as mine, but the answer isn't, you just did the math wrong. I don't care as much about that. To me, the setup is the most important, understanding how to set the problem up. Okay, number 2, this is perfect. All right, you've got a 50-liter container that holds 45 moles of gas at a temperature of 200 degrees Celsius. What is the pressure? You'll notice every time I'm working on these problems, any problem, I always highlight the information that's given and I always box the information I need. It's a really good way to parse and try to figure out what the heck is happening when you have a word problem and you're not sure what to do. So definitely recommend that as a strategy. So we've got the volume, we've got the temperature, we've got the N, and we're solving for P. So Pervner, PV equals nRT. We're solving for P, so let's divide each side by volume. So pressure is equal to nRT divided by volume. Now, we've got our moles is 45. We've got our R is 0.082057 liter atmosphere per mole K. Great. Our temperature, ooh, we've got a problem here. Our temperature is in Celsius. That has to be in Kelvin. So Kelvin is equal to 273 plus degrees Celsius. That's going to be 273 plus 200. It's going to be equal to 473 Kelvin. So that's the number I'm actually going to use. We're going to take this whole thing and divide it by the volume, which was 50 liters. Now we can just cancel out all of our units. I got liters and liters and moles and moles and K, and I'm left with atmospheres, which is just what I want. So our answer is going to be 45 times 0.082057. Let's just delete that one. It's not going to make a huge difference. If you input this number like slightly differently, it's fine. As long as you get kind of close, the math will all work out. I also don't really care if your answer is like off by mine. Like if you put 9.87, okay, cool. I don't know why your answer is different than mine. I don't care. Doesn't bother me. As long as you're in generally the right place, we're good. It looks like our answer is going to be 34.93 atmospheres. That's our answer. Okay, every one of these problems is basically the same. There's sometimes it'll get a little more confusing or less, but I think that gives you a good idea. So you can go ahead and work through some of them. Some of these pages actually have all the answers, which is really nice, or it gives you some conversion factors at the bottom. So use those if you need them. And yep, obviously skip that problem because that's a whole thing. Oh, one other thing I should mention. If you see standard temperature and pressure, STP, also known as, that is literally what it sounds like. It is the standard temperature and pressure for experiments. The standard temperature is 0 degrees Celsius, which is 273 Kelvin, and 1 atmosphere. So if it asks for something at STP, let me see if we can find a problem that does that. There usually are some. Here we go. calculate the volume which 1 mole of gas occupies at STP. So you have 1 mole of gas, you need the pressure and the temperature. That's the pressure and temperature. It's automatic. So, and I believe, do they tell you about STP down here? They don't. But sometimes they do. Anyway, all right. We will talk a little bit more about moles in the next video, but there you are. Thank you all very much. Enjoy.